The generator role is a default role in every proof of justice implementation and allows a given entity to generate and push the next block according to multiple criteria. A generator always refers to another default role called an enforcer, which is responsible for validating parts of a block, specifically the ordering of transactions within it, and providing its approval / the differences in the transaction ordering to the generator to include either fully or partially in the block. Alongside the baseline criteria, one additional criteria appropriate for this role could be that the generator must have a determined number of transaction types in its mempool. In one implementation, this number could be a proof of justice parameter, while in another it could be calculated using a dynamic block size system, which will be elaborated upon in the next video. Moreover, alongside the baseline restrictions, some appropriate restrictions for the generator role could include the number of transactions the generator can include in a block according to its generator level, a sum of blocks generated over time, and the like. In order to generate a valid block, the generator needs to gather some pre-block information. This pre-block information generally includes the full or a subset of the transactions in the generator's mempool, the hash of the previous block, and the like. In most implementations, the pre-block information will also include the Peterson of the generator. In proof of justice, transactions in a block are organized by their partner Peterson. This is a key component of why transactions can be feeless. The organizing is usually done by ordering transactions from the smallest partner Peterson to the largest. However, several organizing techniques may be used according to the implementation, as long as it is replicable by other entities in the network, and that it takes into account the nonce associated with each transaction on top of their partner Peterson. It is also recommended to use one or more fast, efficient, and reliable self-balancing data structures as core components of each mempool to optimize the organizing process. Once the pre-block information has been gathered, the generator signs it, creating a signed pre-block. In order for a block to be considered valid, a comparison list from an enforcer must be obtained and comprised in said block. To do so, the generator would first select an enforcer using the entity selection process mentioned in a previous video. Then, the generator sends the enforcer a message comprising the signed pre-block information. The enforcer, after receiving the message, will do two things. First, it will generate its own Peterson using the Peterson generation process mentioned in a previous video. Then it will validate the message and its content. The first part of the validation will vary greatly according to the implementation. In most implementations, one important part of the validation is to evaluate the distance between the generator Peterson and the enforcer Peterson. To do so, the enforcer would use the Peterson tracking process mentioned in a previous video to determine the distance in blocks between the generator Peterson and its own Peterson. As such, if the distance is above a determined threshold, then something may not be right, and the generator may be acting maliciously. The second part of the validation involves the enforcer gathering the transaction in its mempool as if it was generating a block, in the exact same way that the generator did earlier. Once gathered, it will organize them using the exact same method that the generator ordered the transactions in the received message. The enforcer will then compare its own transactions order with the one in the message to find any differences to produce a comparison list. If everything is fine, the enforcer will then include its Peterson, as well as the comparison list into a second message, sign the message, and send it to the generator. According to the implementation, the second message may contain additional information, such as the hash of one or more relevant portions of the first message. It is then determined if there is a need for one or more other enforcers for the block. This can be done based on various conditions, such as the generator's level, by looking at the number of punished generators over a determined number of previous blocks, by the generator upon getting a recommendation from the enforcer, by a proof of justice parameter, or any other condition relevant to the implementation. If it is determined that the block needs another enforcer, then one is selected using the same process as for the first enforcer. It is also determined if one or more other enforcers are necessary for the current enforcer. Indeed, in one or more implementations, an enforcer itself may need another enforcer to validate its work, especially if the enforcer has a low enforcer level. However, in one or more implementations, there may be no need for an enforcer to have one or more other enforcers validate its work. Without going into the technical details, the process for selecting such enforcers would be similar to the one used to select the generator's enforcer, with some variations depending on the implementation, such as if a comparison list or a transaction list is sent by the current enforcer and used for the next enforcer's comparison, or the like. The entity that performs the next selections will also vary greatly according to the implementation. In one implementation, the second enforcer may select the next one. In another implementation, it may be up to the generator to select its next enforcer. The process is then repeated for each new enforcer until it is determined that the block or current enforcer thereof has gathered all the required enforcers, or until a maximum number of enforcers has been reached. The enforcer selection process can be much more complex based on the implementation of proof of justice. If you are interested in learning more, we invite you to take a deep dive into the generator and enforcer section of the Proof of Justice whitepaper. Once the necessary enforcers have done their duties, the generator compiles the data, adds the one or more enforcer comparison list to the block, signs the block, and broadcasts it to the network. Upon receiving the block, the receiving entity will check to see if it is valid. This will involve checking things like the header and the structure of each section of the block. If a dynamic block size mechanism, which will be elaborated on in the next video, is used, then the size of the block will also be checked. The entity will also check to see if the transactions in the block are valid. Make sure that there is no conflict of transactions with one or more of the previous blocks, that the transactions are organized properly, that all of the signatures are valid, and the like. The validation of transactions may either be done in full by the entity or with the help of the transaction caching mechanism mentioned in the previous video. In case of a block conflict, the entity will determine which block is appropriate to keep based on various conditions, such as which chain is longer, which generator has the highest level for each of the blocks in conflict, and other conditions that are relevant to the implementation. If the block is valid, the entity will add it to its local copy of the blockchain, which will now be one block longer. The entity will then execute and apply the rules on its current chain version, using the rules applying mechanism mentioned in a previous video. It will also make sure that the one or more scores of each entity part of the system are up to date in its local database. The entity might also update its local balances of each currency involved in its current chain version, according to the transactions made in the last block, as well as the block rewards distribution. Indeed, entities that performed role-related actions within a new block receive rewards in the form of newly created units of currency, called block rewards. The purpose of block rewards is to incentivize entities to contribute their time, energy, and resources to the system by performing the various roles required to keep the system running. The amount of block rewards given to each entity is based on its role and may also be based on other conditions, such as the entity's role level. Each role has a weight on the block rewards. For example, in an implementation, the enforcer could get 35%, the generator 30%, the speedsters 15%, the sentinels 15%, and the partners 5%. These weights may be changed through a vote, or by other methods like slashing mechanisms, depending on how proof of justice is implemented. For example, one way to slash rewards would be to have them every determined number of blocks, depending on the available reward supply. Indeed, in one or more implementations, the number of available rewards can sometimes increase if a burn mechanism is used. In most implementations, the weights are, by default, defined as proof of justice parameters. Different block reward systems may be used in proof of justice depending on the implementation. For example, while in one implementation the only rewards given are the core coins of the blockchain, in another implementation, tokens created by proof of justice could also be included in rewards depending on things like how many transactions in the block involve those tokens. For example, If there are 5 transactions in a block and one is for coin A, 2 are for token B, and 2 are for token C, the rewards would be 1 coin A, 2 token B, and 2 token C. The reward for each token would be determined when the token is created and, in some implementations, could even be adapted using a voting system like the rule updating system mentioned in a previous video. This system creates competition between tokens on a proof of justice-based blockchain, encouraging the creators of each token to market their token to attract more users. This would create publicity for the proof of justice-based blockchain. Additionally, this system allows for delaying the time when the main coin's maximum supply is reached, which can be very useful based on the implementation. Some implementations would only have the tokens be weighed, while the native coin would always be rewarded fully. The reward for each token is set when the token is created and can be changed using a voting system like the one mentioned earlier that updates rules. Some other implementations would have every token created on a proof of justice-based blockchain used as block rewards without the transaction weighting mechanism. If transactions in a block are not feeless, the fees could be added to the default block rewards or distributed to specific entities based on the type of transaction. For example, a transaction that involves one or more entities with the code reviewer role could allocate a large percentage of the fees to the code reviewers, even if it is not the default rewards weight. If a dynamic block size mechanism is used, which will be explained in the next video, then the rewards distribution could be affected. BB Inventions, high-tech research for curious minds.